Have you ever hit a problem with more than two variables and just stared at it? Well, if you have, you are in exactly the right place. Today, we're going to master multivariable linear systems. This is the method, the systematic way, to find that single point where things intersect in three-dimensional space. Let's jump right in. So, here's our game plan. First, we're going to build on what you already know about 2D graphs and take it into 3D. Then, we'll talk about the main goal of every problem, which is getting it into something called triangular form. After that, we'll walk through solving a problem together, step by step. And of course, we'll cover the common mistakes so you can avoid them, and we'll wrap up by seeing how this math actually powers our world. All right, first section. We are officially leaving the flat page and jumping into the world of three dimensions. And trust me, this is where it all gets so much more interesting. Okay, think about it like this. You're already an expert at finding that one little point where two lines cross on a graph, right? But now we're not dealing with simple lines. We're talking about planes, these huge, flat sheets that stretch out forever in 3D space. Our new mission is to find the one single point in all of that space where three of these planes all intersect. It's the same idea, just with a whole new dimension. So how in the world do you handle that extra complexity? Well, you need a clear target, a destination you're aiming for with every single problem. And for us, that destination is called triangular form. Just look at this thing. It's so clean, so elegant. See that stair-step pattern? The bottom equation has just one variable, the one above it has two, and the top one has all three. And that's not just to make it look pretty. That structure is the absolute key that unlocks the solution and makes the final steps incredibly easy. And that brings us to the best part, the payoff. Once you've done the work to get your system into this beautiful triangular form, believe me, the hard part is totally over. The rest is just a super straightforward process called back substitution. And it's pretty much exactly what it sounds like. You know, the process is practically automatic. You start at the bottom and solve that super simple last equation. Then you take that answer, you plug it into the equation right above it, and solve for the next variable. You just keep working your way back up the triangle. It's like a domino effect, and it's so satisfying. Okay, enough theory. Now that we know our goal and our final move, let's actually put it into practice. This is the guided walkthrough, where we're going to solve these systems together. Let's start with an easy one to warm up. This system is basically a gift. It's already in perfect triangular form for us. Look at that bottom equation, z equals 2. The first piece of the puzzle is just handed to us. So we can hit the ground running and start our back substitution immediately. So we know z is 2. We plug that into the middle equation to find out that y is 3. Then we take both z equals 2 and y equals 3, plug them into the top equation, and boom, we get x equals -2. And there it is, the solution, -2, 3, 2. That is the one single coordinate in 3D space where all three of our planes meet. Okay, warm-up's over. Time for a much more realistic problem. This system is messy. It's not in that nice triangular form. So our mission, should we choose to accept it, is to systematically whip it into shape using a method called Gaussian elimination. Now the key here is to be methodical. Our first target is the x variable. We want it gone from the second and third equations. And we can do that by cleverly adding or subtracting multiples of that first equation from the other two. Our whole goal is to make those x terms just vanish. And after that first step, look at that. Our system is already looking so much cleaner. We've only got x in the very first equation. Now we just repeat the process. We target the y variable using our new middle equation to eliminate y from the bottom one. And just like that, our system is in that perfect, easy-to-solve triangular form.
And now for the reward for all our hard work. Our final equation tells us z equals 6. We plug that back in above it to find y equals 8. Then we plug both of those values into the top equation to find x equals -8. And there's our solution, -8, 8, 6. All that work of elimination really paid off, didn't it? It made these final steps a piece of cake.
So that's what happens most of the time. But every now and then, something weird happens while you're eliminating variables. You might simplify everything down and end up with a statement that's just always true, like 0 equals 0. What on earth does that mean? Well, it's not an error. It's actually a clue that we're dealing with a really special case. Let's check out this system here. If you look really closely at those first two equations, do you see it? Equation 2 is just equation 1 with every single number multiplied by 2. It's the exact same information, just in disguise. This tells us we don't really have three unique planes. We effectively only have two. So if this happens, it means the planes don't just meet at a single point. No, they actually intersect along an entire line. And a line has an infinite number of points on it. So how do we write an answer with infinite solutions? We use what's called a parametric solution. Basically, we let one variable be a parameter, we usually call it t, and then we describe the other variables in terms of t. This gives us a formula for every single point along that line of intersection. All right, now that we have the methods down for solving all these different types of systems, let's talk about how to make sure you get the right answer every single time. Here are a few pro tips to help you avoid the most common pitfalls. First, and this is the biggest one, watch out for simple arithmetic errors. It is so easy to add when you meant to subtract. Just double-check your work as you go. Second, when you start back substitution, always start from the bottom equation and work your way up. Don't even think about starting anywhere else. And finally, remember what 0 equals 0 means. It's not a mistake, it's your signal that you've got a dependent system with infinite solutions. So, you might be thinking, okay, this is a cool puzzle, but why does it matter? Well, this might seem abstract, but this mathematical tool is incredibly powerful, and it's used to solve some very real, very important problems. Let's take a look. Seriously, this is not just some textbook exercise. Electrical engineers live and breathe this stuff. The technology you're using right now, your phone, your computer, anything with a circuit board, it was all designed and tested using multivariable systems, just like these. So here's how it works. Using rules like Kirchhoff's laws, every single loop and every junction point in an electronic circuit creates its own linear equation. But the unknown variables aren't x, y, and z. They're the electrical currents, which they call I1, I2, I3, and so on. By setting up the system of equations and solving it, engineers can figure out the exact flow of electricity through every single part of a device. It's amazing. So, I want to leave you with this thought. You now have this incredibly powerful tool for untangling complexity. And it's not just for planes in space or currents in a circuit. Think about economics or shipping logistics, or even figuring out complex chemical mixtures. What problems in the world around you have all these interconnected variables that you could now, maybe, start to model and solve?